Okay, hi everyone. My name is Dale Kim. I am the Senior Director of Technical Solutions at Hazelcast. So thank you to the MemVerge folks for inviting me to speak. I want to talk about some of the use cases that are made more effective with Hazelcast and MemVerge working together. And so what I'll do is first talk about what is Hazelcast, and I'll go through that fairly quickly, but then I'll talk about how Hazelcast and MemVerge work together, how they fit together in the stack, and then talk about some of these example use cases. Now, to simply describe us, Hazelcast is an open source software platform designed for ultra high performance intelligent applications. And what that essentially means is that you can build and deploy applications within the framework of what we provide. They're intended to be very high throughput, low latency, and generally do things like run machine learning models. They do a lot of number crunching. There's a lot of business logic. So more than just some of the straightforward, simple apps that are doing ETL, but rather some of these more complicated processing that you might do on streaming or batch data. So it combines the distributed in-memory computing capabilities with stream processing. So it's all about real time, it's about speed. It's generally about adding these capabilities to your IT infrastructure, your existing infrastructure, so that you get some of these modern capabilities without having to overhaul your system. So we're ideal for the cloud, on premises, or at the edge. So here's the general architecture of our system. You'll see Hazelcast in the middle, and then there are components to the left, right, up, and above. And I'll just quickly go through each of these components to give you a sense of where we fit into an IT infrastructure. And so as I mentioned, Hazelcast combines two capabilities, the stream processing or processing in general. So streaming is certainly the unbounded inflow of data. Batch is a bounded flow of data, but the type of processing that can be done is very similar, whether it's streaming or batch. And then there's the in-memory component that is very good for storage, but also for in-memory processing. So there's a lot of computation that can be done in memory that's far more advantageous to do in a cluster versus in a standalone application. And so on the left represents the data sources. So these are the types of data that we operate on. They might be streaming data coming from an IoT device that's stored in Kafka. It might come from a data warehouse, or it might even come from Hazelcast itself. So some data could be stored in memory. We do some processing and write it back out. So again, this is the data that we operate on that normally represents that real time or that fast responsiveness. And then to complement that, we have the data sinks. And so for both the sources and the sinks, we have a collection of out-of-the-box connectors to integrate with these existing data platforms. And so after we do some processing from the data from the sources, now we can deliver it to something else, including to ourselves within the memory store, so you can do more processing on that downstream. And at the top level is essentially the APIs. So the client libraries where you can build applications or build interfaces with other applications that talk to our system. So whether you have a microservice or some type of end user interface, you can use languages like Java, C++, Go, C#, and so on to build these interactions. And essentially what this is handling for us is the interaction that we're managing. So the interaction from an external application or from an end user that we're managing and integrating with the data that you have inside the store. And maybe there's some processing along the way. And the final component are the systems of record. And so we generally integrate with these large stores, whether they're your legacy databases, your data warehouses, or data lakes, pull in that information as necessary and use it for reference data to help out with creating context for the interactions with our system or with the data that we operate on. So that's an important part of this overall architecture, and you'll see how that becomes important as we work with MemVerge. And so we're really good for the notion of event-driven architectures, and we're seeing that growing quite a bit, particularly in the context of AI. So a lot of these AI or machine learning inference environments will take streaming data, do some processing, and create some score, and then pass it on to the next process in the flow. And with these traditional event-driven architectures, you typically have two components that are vital to the entire system. One is the stream processing software. And so that's depicted at the top. And the ones available today tend to be pretty complicated. And that's just the cost of doing business. But there's a lot of work to be done there in terms of trying to integrate with the other components, like the external data stores at the bottom. And that represents a copy of the systems of record that deal with reference data. So you know that event data tends to be fairly sparse. You might have information like a machine ID, but you need a lot more context than that. And that's where you turn to the reference data for enriching that so that you get full analytics on that. And what Hazelcast has done is combine the two components so that you eliminate the latency associated with reaching out to an external data store, even if that data store is an in-memory database or some high-speed store. You're still going over the network. And so what if you could integrate that component into the same nodes that you're doing the processing and eliminate a lot of the complexity? And so one of the design principles for Hazelcast was the simplified development aspect so that we provide our software in the form of a Java jar file. And so it's very easy to deploy, no external dependencies as part of the overall deployment. And so that in combination with the in-memory computing component, now you have stream processing and you have the in-memory component as well working together within one framework. And so here's how the two pieces work together, where you have MemVerge and whoops. So if you start at the bottom with a computer server, you have some allocation of Optane and DRAM working together. You have the operating system on top of that. And then for us, MemVerge is essentially that abstract layer that represents that huge allocation of memory. So from our standpoint and from any standpoint from any application, you just know that you have a lot of memory. And being an in-memory computing platform, that's a good thing for us. And so you might ask, so what's the difference between using just MemVerge within your own custom applications and having Hazelcast in the middle? Well, as I talked about where we fit into the stack, there's some memory coordination that has to be done with the systems of record. So we provide the framework to simplify any manipulation that you'll do on that reference data and then write back out to the system of record. There's building the stream applications, which when you do things like create windows and create aggregations within those time windows or being able to identify late arriving data, we handle that for you. So we simplify the notion of distributed streaming applications. The sharing memory across all nodes is really important. So MemVerge is really good for scaling up. So if you get a ton of memory within a single node, that gets you a long way for a lot of performance advantages. And now if you want to scale out across multiple servers and also get some replication so that you increase high availability, you can do that with us, as we'll handle that type of distributed clustering. And finally, the multi-node processing. So in addition to the data being distributed, but being able to distribute processing across multiple nodes and having them coordinated together is an important aspect for some of these high-performance applications. One use case I want to talk about, and there are basically two broad architectural use cases with MemVerge. And the first one is about just more memory. What can you do with that? And a classic AI use case is fraud detection. And so a lot of companies have transactions where you want to run fraud detection that's machine learning based. And one company determined that instead of incrementally evolving their machine learning model, they decided to run multiple models run from different teams at the same time and create a composite score. And that gave them a better overall fraud score that not only reduced fraud, but helped to identify the false positives as well. So it was a two-way win for them. The only way they could do that, being able to run multiple models at the same time and create this composite score, was by having improved performance headroom. And one way they got it was with Hazelcast, and by having a lot of memory available, not only for the performance for the lookup data, but also having more data richness for the enrichment aspect and creating more context allows them to create more accurate models. So having that model.
So Dale, is MemVerge providing the cloning of the data for these multiple models? Is that how it works, or is it just that each of these servers has MemVerge in there and they can bring all the data in and therefore process it a lot quicker?
Yeah, it's that. So
okay.
We're basically seeing it as we have a huge allocation of memory thanks to MemVerge. And we do the processing on our own and independently of any of the snapshotting or cloning they might do.
All right, thanks.
Sure. And so that's one use case in where big memory is a good thing for our server. I borrowed this slide from the MemVerge folks, and this is another use case talking about how the cloning will enable high uptime and reduced downtime. And so in Tesla San Paulo is a big old established bank in Italy, and they used Hazelcast as part of what we call a digital integration hub. So it's a data layer between some of their newer applications and newer customer channels like web and mobile to the back-end systems. And like many organizations, you have an existing back-end system, handles your core operations, it runs well, you don't want to muck with it. What can you do to add new channels without changing or overhauling anything? And that's where Hazelcast comes in. We're that middle data layer that accelerates access to data and accelerates query responses and so on. Now, with Intesa Sanpaolo, the interesting thing is sometimes in their area, they encounter rolling brownouts. And that means that the entire system goes down. And if there's a lot of aggregated and filtered and indexed data in memory, if they have to reread all of that and reprocess it, that could take a long time. And so we're looking at improvements from originally 15 minutes of downtime. And considering these are customer-facing applications, that could have huge impact in how they're being perceived and how customers want to do business with them. Reducing that by a factor of 70 down to 13 seconds means that they still have to deal with the downtime of the brownout, but if they can get the entire system ready to go and the in-memory rehydrated in 13 seconds, that means they're good to go really quickly. And so one architectural pattern that I want to talk about is a flow of getting a ton of data, reducing it based on some user request, and then ultimately storing it in some data mart for ongoing specific drill down analytics. And so if you look on the left, this is an example taken from a capital markets company that has millions of trades per day that they store in their own system. And they want to identify what are some of the patterns that are occurring throughout the day, especially if there's some volatility in the market. But this is a risk team that doesn't necessarily have a huge budget. So they're looking at trying to do something that's a little bit more cost effective. Certainly Hazelcast fits in with that story. MemVerge does as well. And so what they want to do is run a query that filters the data. So instead of reading in the entire data set, they read a specified data set. That data is indexed, put inside memory, and now they've essentially gotten an in-memory data mart for them to do ongoing analytics. And so rather than having to wait a long time or end-of-day batch processing, they have something near real-time to do the processing. And so this is from a high level, this notion of getting a lot of data and then filtering down to a smaller set and then moving on. The relevance of AI in this case is some of the things that we've plugged in that take advantage of big memory. And so if you drill down a little bit, you'll take data from a source, and then Hazelcast will read in that information, do the appropriate data wrangling for that information, and then send it out to a machine learning model. And then once it gets some score, could potentially do some more processing. So this is really good for things like anomaly detection or for recommendations. And then ultimately put it in some store where some end user can do some processing. Or the system can do something automated for you. So some type of automated process related to manufacturing and assembly line QA would be possible as well. And so the real problem that we're trying to solve here is the challenge of getting a machine learning model into production. And so, because of the two sides of training and inference, we focused more on the inference side. Now, on the training side, I see a lot of opportunities for MemVerge to be able to help out there, especially since with a ton of training data that you have, one of the bottlenecks tends to be reading it all in. So putting that in memory, I think, would be a clear win. What we've done in terms of our platform is help out on the inference side. So how do you get that model that a data science built, especially if that model's in C++ or Python, and put that into production without requiring a ton of coordination with the DevOps folks? And so in my obligatory complicated process diagram, I think there's two main takeaways from this. One is that there's a whole bunch of stuff going on in the Hazelcast cluster that is largely abstracted away from the DevOps folks, so or the developers. And so the developers will write a data processing pipeline that will take data, process it in a declarative format in our API. So it's fairly easy to write that. Behind the scenes, each of the subtasks along the way are deployed across the various CPUs in the cluster, some of which are allocated to machine learning scoring, and then ultimately that's dumped out to some end destination. So everything that in the Hazelcast cluster is being handled by the declarative code that the developer has written. The other takeaway is the simplicity for the data scientists, so that Python code is simply, once it's created, once it's been trained, is put into a file system folder, and then the pipeline that based on Hazelcast will pick that up and deploy it to each of the nodes that are handling the machine learning scoring. And that means that the Hazelcast infrastructure is also maintaining the Python VMs and all the coordinations so that everything is being done behind the scenes. So if the Python VM happens to crash, then that workload is redirected to another node. So the high availability, the business continuity aspects are being handled all by themselves. And what this means is that the DevOps folks, the developer folks have their own responsibilities. There's some coordination in terms of what that pipeline will look like, but they have their set of responsibilities. The data scientists can work independently and potentially deploy their code free from the rest of the IT folks, and thus help to further expedite and accelerate this notion of machine learning inference. And certainly that contributes to a lot of the types of experimentation that the data scientists want to pursue, so that they're not always blocked by some difficulties in getting the code into a production environment. This is a quick slide on performance. The typical way that you deploy is over a REST environment into a separate cluster. And we show dramatic improvements from 5 operations per second to about 97,000 operations per second as a result of using our framework. So hopefully that's pretty self-explanatory. And the last thing I want to talk about is just this notion of rapid job upgrade. And whenever you want to deploy a new version of a job, you want to make sure that there's no data loss, there's no downtime. And we have a mechanism that simply, interestingly enough, takes a snapshot in memory of the state of the stream, replaces the old job with a new job, and then it continues the processing by applying that new data that was captured in the snapshot into that new version. And so you get that continuous processing after inserting a new version of a job. So I know that I went through a lot of material fairly quickly, but I hope you got a good sense of where we fit in and how the big memory and the snapshotting capabilities of MemVerge work quite well with an in-memory computing technology. So thank you very much for watching.